Welcome to part 2 of my lecture series on residuals in CFD. In part 1 of this lecture series, we looked at basic residuals, what they physically mean, and how they're calculated by CFD codes. Now, if you've taken a look at the user manuals and in online forums for CFD, you'll often find things referred to such as scaled residuals, normalized residuals, and relative residuals. And this can be quite confusing as it's not clear what these terms actually physically mean and how they're calculated by CFD codes. I'm going to clear up a lot of this confusion in today's talk by talking about scaling residuals. I'm going to go through the process and explain to you why residuals are scaled, why we need to do this, and how the scaling process is actually carried out by CFD codes. So by the end of this talk, you can have an even deeper understanding of what residuals are, which is ultimately going to help you when you're assessing the convergence of your own CFD cases and general understanding of CFD codes in general. So let's jump straight into the talk. So let's start things off with a quick recap of what we talked about in part 1 of this lecture series. Now you'll remember that we looked at the simple example of 1D heat conduction in a bar where we have a 1D bar, and at both ends of the bar we have a fixed temperature. On the left side we've got a hot temperature, and on the right side we've got a cold temperature, and we've got no heat sources in the bar for this example. And when we divide the bar up to into 4 elements, we find that the temperature profile of course varies linearly between the hot and the cold end of the bar, and heat will flow from the hot end of the bar through to the cold end of the bar. And we could solve this problem analytically by hand, but the way we chose to do it to show how CFD codes work is we used the finite volume method, and we applied conservation of energy for each individual cell in the mesh, and resulted in a matrix equation, AT equals B, and solving that matrix equation will give the temperature T1, T2, T3 and T4 at the centroid of each of the 4 cells in that mesh. Now, you'll also remember that CFD codes generally use an iterative process to calculate the solution for the temperature equation and the other equations that are solved. And so what that means is that at any particular iteration in the solver, the solution does not match the final solution. And a way that we can think about this for our temperature profile is that when we have no heat sources in the bar, we expect the temperature profile to vary linearly between the hot and cold ends of the bar. But while we're converging, that temperature profile will not be linear. And so what that means is if we think of any particular cell, now the gradient of the temperature profile while we're converging between those 2 adjacent nodes will be linear, but it won't match through the left and the right faces of the cell. And of course what that means is that because the gradient is different, that means that the heat flux out of the left face of the cell and the right face of the cell don't balance. And so we have a local energy imbalance in each of the cells in the mesh while the code is converging. And what we can then do after we've solved a particular iteration in our iteration process is we can take the current solution for that temperature vector T1, T2, T3 and T4 and substitute it back into the equation AT minus B, and that will calculate the residual vector for us, which is here on the slide for the 4-cell mesh R1, R2, R3 and R4, where each of those R values gives the local energy imbalance in each cell in the mesh. And of course, as the solution proceeds and the iterative solution gets closer to the final solution, those energy imbalances will reduce towards 0. And when those energy imbalances are reduced below some certain tolerance, we can be happy that our solution is iteratively converged to some tolerance. Now, the focus of today's talk is going to be taking that idea of the residuals and applying a process called scaling to the residuals. And what I want to do before showing you the process is to explain to you why we need to scale the residual vector. And the way I'm going to do this is just by considering 2 very similar examples, which you can see here on the slide. In both cases, we've got the same case that we looked at before, but we've got the 1D heat conduction in a bar between 2 fixed temperatures. And for the case on the left, I've got the hot end of the bar at 31 degrees C and the right end of the bar at 30 degrees C, so a very small temperature difference there, only 1 degree. And in the case on the right, I've got the temperature of the left end of the bar is really hot, say 200 degrees, and the temperature on the right is 30 degrees. And so, of course, because the wall temperatures are different, we expect the gradient of that final solution to look different when we solve the problem. And in both cases, we've got no heat sources in the bar, so we're still going to get a straight line variation of the temperature between the two sources. Now, of course, because the temperature difference is very small in the left case, the gradient's going to be very shallow, whereas in the right case, the gradient's going to be a lot steeper. Now, suppose that we were carrying out an iterative solution process and we looked at the solution during a particular iteration in that iteration process. And if we look at the case on the left, for example, firstly, and we were to look at those heat fluxes out of the left and right faces of the cell, for that cell that's shaded in grey, you can see that through the left face of the cell, we've got a heat flux of 0.1 watts, and then out of the right face, we've got a heat flux of 0.11 watts. Now, of course, there's a local energy imbalance here, and that energy imbalance is the residual, which for the case on the left is 0.01 watts. It's just the difference between the heat out of one side of the mesh and then the heat flux out of the other face of the cell in the mesh. Now, if we just flick over and look at the case on the right, we do exactly the same thing again, but in this case, for example, we've got 100 watts coming through the left face of the cell, and we've got 100.01 watts coming out of the right face of the cell. Now again, the difference between those two fluxes gives us the energy imbalance, which is the residual for that particular cell, and in this case we also find that the residual is 0.01 watts. So for both of these examples, we can see that those cells in the mesh have the same residual, but the question for us as a CFD analyst is, are both of these cases equally close to convergence? Because we use the residuals to judge convergence at the moment, and both of these cells have the same residual. So are they both as close to convergence as each other? Now, the trick and what you'll notice is that actually, if you compare the energy imbalance in that cell, or the residual, relative to the flux of energy through that cell, what you find is that the residuals are actually very different. So if you take the case on the left, and we've got a residual of 0.01 watts, but then if you divide that by the flux of energy through the cell, which is 0.1 watts, you find that as a percentage, the energy imbalance is 10%. So of all the energy that's passing through the cell, 10% is being lost because we're not yet converged. We've got a relative or percentage energy imbalance of 10% in that particular cell. Whereas if we look at the case on the right, we've still got the same residual, 0.01 watts, we've still got the same energy imbalance, but relative to the 100 watts of energy that's passing through that cell, the scaled residual is only 0.01%. So the case on the right is actually a lot closer to convergence, because the energy imbalance relative to the total energy passing through the cells is a lot smaller. And this concept is actually what a scaled residual is. So you can think of a scaled residual as the percentage of energy lost or gained in a particular cell in the mesh during the iteration process. So that's the basic idea. Now we're going to expand on it a bit more and think about maybe how that might be calculated. Now, before I do that, I just want to put a quick flag in to remind you all that I'm just considering the energy equation in this particular talk, but the same idea can also be applied to the other equations that are solved iteratively by the CFD solver. So if you were to solve the U momentum equation, for example, using the same approach, you'd find there'd be a residual in each of the cells in the mesh, and that residual represents the local force imbalance in that particular cell in the x direction. So you can see in the small image on the right, we could have just applied this same idea to the U momentum equation, where we'd have 30 newtons of force acting on the left face of the cell and 30.01 newtons acting on the right face of the cell. So in that case, the residual is 0.01 newtons. And what we'd be looking at with the scaled residual is the percentage force imbalance relative to the force acting on the cell, or the momentum flux passing through the cell. You can also think of it that way. So the idea that we've introduced here with a scaled residual is quite neatly summarized by equation 2, and you'll find this sometimes in CFD manuals if you look at the manuals, where all we're doing is we're taking that raw unscaled residual in each cell in the mesh R, and we're dividing it by n, where n is called the scaling factor. And we've seen from that past example in the past few slides that what we want n to be is we want n to be representative of the heat flux that's passing through a particular cell, or the momentum flux that's passing through a particular cell, so that then we can scale that raw residual by the flux passing through the cell. So we've got an idea of what it should be, but how is the scaling factor calculated? Well, it turns out there are actually two different ways that you could calculate the scaling factor, and the first way is to do it manually, and this is perhaps the most direct approach. Now, if you had a very simple problem like the 1D heat conduction in a bar that we've been looking at today, where the left end of the bar was at 200 degrees, say, and the right end of the bar was at 30 degrees, you could do a hand calculation to work out what the total heat flux would be through that bar. And the formula, of course, would just be Ka, so K being the thermal conductivity, A being the cross-sectional area of the bar, and L being the length of the bar, and then multiplying that by the temperature difference. This is just Fourier's law, and this would actually get you the heat flux through the bar, and you could use that heat flux to scale your residuals when you're carrying out an iterative process with a CFD solver. And you can do this for other quantities if you have general CFD geometries and maybe you have inlets or various quantities that you could work out by hand. You could get a pretty good guess of what you thought a manual scaling factor would be. And another example would be if we took our same heat conduction in a bar problem that we had before, and rather than having a fixed temperature of 300 degrees on the left end and a fixed temperature of 30 degrees on the right end, say we had a Dirichlet boundary condition, a Neumann boundary condition on the left end of the bar where we apply a heat flux rather than a fixed temperature, then we could see quite easily for this problem that 1500 watts is going to be passing through the bar. And so an appropriate scaling factor, if we were solving this problem iteratively, would be a heat flux of 1500 watts. Now, how would you do this in practice with a CFD code? Well, different CFD codes have a variety of different settings for residuals, and this is part of the reason why I'm going through them in the talk today, so that you understand them and you can work out what boxes you want to tick and activate to do certain things. Now, if you wanted to do a manual scaling yourself, what you would do is set the residual output to unscaled, so the CFD solver would be producing unscaled residuals, which would just be those raw energy imbalances in each cell. And then what you would do is divide those values by the scaling factor that you calculated manually by hand. And that would give you your scaled residual for you to interpret. Now, naturally, this is quite a cumbersome process, and having to divide things yourself, or sometimes in CFD codes you'll have an option of a scaling factor you can input yourself, and you could just input it into the code. But what you probably notice is that for the majority of real cases are often very complex, and it'd be difficult to work out what a representative heat flux or momentum flux would be for your particular geometry, particularly if you're three-dimensional and you have lots of different surfaces and things. And generally when CFD codes are written and set up, they have to assume that they're solving a very general problem where entering a manual scaling factor is not possible. And so CFD codes actually have to come up with some kind of automatic way of calculating a representative flux through the geometry for you. And that's the second option that I want to talk to you about today. That's the second option of calculating that scaling factor. And I've chosen to call this a general scaling factor, but you may see it referred to as other things in CFD manuals. Now, if you go back to the problem that we're considering, we have 1D heat conduction in a bar with 4 cells, which is governed by this matrix equation that we set up. We've got AT equals B, and solving that will of course give the temperature at the centroids of each of those cells in the bar. Now, for real CFD problems, you will also have a similar matrix equation of this form. It of course may be a lot larger depending on your geometry and your mesh and the number of cells, but the general form AT equals B will still be there. And so a better way to frame the problem now would be, seeing as for a general CFD problem, we may not know how many inlets or outlets or walls we have, but we know we're always going to be solving a matrix equation of this form. Can we extract a scaling factor directly from the matrix? Can we look at the terms and the coefficients in the matrix and somehow pull out a scaling factor that we can use? And recall that for this problem, the heat flux in general is given by Fourier's law. So Q is generally given by K as a thermal conductivity, A an area, delta X, so a difference between 2 points, and a temperature difference. And so is there a way that we can somehow pull out a representative heat flux from the matrix equation itself? Now, if we think back to the previous talk, what did we do when we set up the matrix equation? Well, you'll remember that each row of the matrix multiplied by that temperature vector is actually an expression of conservation of energy for a particular cell in the mesh. So if I think of that second row of the matrix, for example, that's just conservation of energy for the second cell in the mesh, where that first term there, Ka over delta X, T1 minus T2, is the heat flux out of the left face of the cell, and then Ka over delta X, T3 minus T2, that's the heat flux out of the right face of the cell, and then Q source, which ends up in the B vector, is just the heat source in there. So even just looking directly at this form of conservation of energy, we get an intuition that we might be able to do something clever with the coefficients of the A matrix and the temperature vector to kind of pull out a heat flux that we can use to represent the heat flux passing through our bar in this problem. And this is what I talked about before. So how would we go about doing this? Well, if we think of our conservation of energy equation we have there in equation 5, remember that when we assembled the matrix, what we did was we rearranged that conservation of energy equation in terms of the unknown temperatures, T1, T2, T3, and T4, and collected the coefficients. So we moved from equation 5 to equation 6 and collected all those coefficients. And then the Ka over delta X's, they became the coefficients of the A matrix, and the T's, they're just the temperatures for the temperature vector. So it's clear that we're quite close, and you can see that we just need to be careful perhaps about how we pull those coefficients out, and we might be able to get a representative heat flux from them. So now, the most obvious thing to do would be to think, well, what would happen if I just multiplied the row of the A matrix by the temperature vector? Because that's essentially what we've done, is that's conservation of energy, but then we've rearranged it, and that's become that second row of the A matrix multiplied by the temperature vector. Could we just use that? Would that give us the heat flux through the second cell in the mesh, for example? And that's the bit that's highlighted there. And what this is going to give us is the QL, which you can see there in the small diagram, and the QR out of the right face. So we're just considering the A matrix and the T vector. We're not considering the B vector because that's the source term, the volumetric source term. And we just want the flux through the cell. Now, actually, if you think about this problem carefully for what we've got in our problem, we don't have any heat sources in the bar. And so what that means is that when we're very close to convergence, the heat flux out of the left face of the cell is almost going to equal the heat flux out of the right face of the cell. And in this example, I've got minus 5 watts coming out of the cell on the left face, and then plus 5 watts coming out of the cell on the right face. And actually, the product of that second row in the matrix and the temperature vector actually gives you the net flux out of the cell, which in this case is approximately equal to 0. So we can't actually use the product of that second row in the matrix and the temperature vector, because if we multiplied these together, we'd find that the net flux was about 0, and that's not actually what we want. If we use this, of course, for the scaling factor, we'd get a divide by 0 error, or very close to that. What we don't want is we don't want minus 5 plus 5, we actually just want one of those. We would like just the plus 5. That's another way to think about it. is that we don't want to sum all those heat fluxes together. We actually just want one flux that's representative of what's going through. So we have to think a little bit more carefully about how we might extract a scaling factor from the matrix. And this slide is just to summarize really what we've done here. If you think of that same equation, that part on the left, so the Ka over delta x, T1 minus T2, that's going to give us the minus 5 watts coming through the left face, and then the Ka over delta x, that's giving us the plus 5 watts going out the other side. So if we added both of these together, or took the second row multiplied by the temperature vector, that's going to give us 0. So we actually don't want to use the entire row. Could we do something better? Maybe we could just use part of the row, or maybe even just the diagonal coefficient by itself. And so what happens if we do that? Why don't we just take A22, that's the diagonal coefficient for the second cell, and multiply that by the temperature of the second cell centroid? Well, if we actually substitute in the terms to see what they represent, we can see that A22 times T2 is Ka over delta x plus Ka over delta x T2. So you can see we're almost there. We've got the right sort of terms in there that give us something that looks like Fourier's law, and we want something that's Ka delta x over T2 minus T1. But what most of you will notice here is that actually we can't just take the diagonal coefficient A22 and multiply it by T2, because actually what we need is we actually need a temperature difference. We're almost there, we're so close. We need a T2 minus a T1, or minus some temperature difference. So we've almost got a representative heat flux by taking that diagonal coefficient, but we're not quite there yet. We need a temperature difference. And why is this important? Why is this important that we take the temperature difference? Well, what I wanted to do is just give you here a simple example which should help explain what we're trying to do here. If you think again of the temperature variation through this bar, but this time we've got some heat source in the bar, and so the temperature vector is not linear. In this case, it takes the form of a quadratic. Then what you'll see is that if the left end of the bar is at a temperature of say 300 and the right end of the bar is at a temperature of 299, the actual temperature at the centroid of cell 2, for example, is about 300 Kelvin, but the temperature difference between T2 and T1 is only about 1 Kelvin. So it's 2 orders of magnitude lower. And it's that temperature difference that actually governs how much heat is passing through the bar. Because of course, if the entire bar is at a fixed temperature, you're not going to get any heat flowing. It's the temperature differences that we need. So what we can see now is that we've reduced our problem down and we've almost finished it. We've almost found a way to get the heat flux, a representative heat flux through the bar directly from the matrix equation. But what we need to do now is find a way to get a good representative temperature difference. And what I thought I would do before going on is actually just do a quick recap of what we're talking about here, because it can be quite easy to get lost because there's a lot of technical detail on looking at the equations. Just a reminder, what we're doing is we've got the residual in each of the cells in the mesh R, because we've solved an iteration of our CFD solver, we've calculated a temperature vector, we've substituted it back into AT minus B, and that's given us the energy imbalance in all of the cells in the mesh. And what we want to do to assess convergence is to scale those residuals so they're expressed as a percentage of the energy flux passing through the bar. And we found that a good way to do this for a general CFD problem, where we perhaps don't know what the heat flux through the bar is, or we've got a complicated geometry, a good way of getting a representative heat flux is to take the diagonal coefficient of the matrix, AP, and multiply that by some representative temperature difference, because it's the temperature difference that causes the heat to flow. So the question all boils down to now, how is the temperature difference calculated? Now, I'm glad that I've summarized that for you, because it actually turns out that the majority of CFD codes, when you look through the manual or you look through the source code for how this representative temperature difference is calculated, there's often not a lot of information given on how to do this. And in ANSYS CFX, for example, you'll just find that equation in equation 8 for the scaled residual, and you won't actually find any further information. And so we don't actually know how the representative temperature difference is calculated, but for us, that's okay, because what we're trying to do as CFD users is just to understand how the CFD code works. Most often we're not actually trying to code our own CFD code, and so we don't need to know exactly how to do this. And I may look at some specifics in a future talk, but for now I just want to give you an idea of how you might calculate a representative temperature difference and use that to scale your residuals. So one way you could do this is to subtract the average. This is a very simple method which you could use, and if you think of your temperature distribution in the bar, which you've just calculated as part of your CFD solution, if you take the average of that temperature throughout the domain, and of course this will work for a complicated domain as well as a 1D bar, and then if you subtract that from the temperature field, quite easily what you can see is that you've now isolated the temperature differences relative to the mean. And you can see in that graph on the left, T minus T bar is now only 1 or 2 Kelvin, and this is the temperature difference that we're interested in for calculating a representative heat flux. And then once you've subtracted that mean, what you could do is you could just go through the mesh and calculate the magnitude of the temperature difference and then take the average of that. And that would be quite a good way to get a representative of the heat flux through the bar, because in a complicated CFD domain, temperature differences are going to be different everywhere, and so you'll get some large heat fluxes, some small heat fluxes, but having the average of all of those would give you a good representation of the magnitude of how much heat is flowing through the bar. Remember, we just want to know, are we around 100 watts or are we around 1 watt of heat through the bar, so that our residuals are scaled sensibly for us to judge convergence. Another way you could do this to get a temperature difference is just to take the difference between the maximum and the minimum. And if you have a domain where the temperature differences are all very similar, this would also give you a good representation of what the heat flux through the bar is. It might be a bit larger than the previous guess of what the heat flux through the bar is, but generally for us, we don't actually care about what the actual heat flux through the bar is at this stage, because remember, you're just churning through the iterations of the CFD process, and you just want a quick look to see how close do I think my solution is to convergence. And because we're using a representative heat flux, this is one of the reasons why the exact number of the residuals isn't important when you're assessing convergence. So if you had a scaled residual of 2 times 10 to the minus 3, for example, or 4 times 10 to the minus 3, for example, the exact value isn't really used to assess convergence. Usually as CFD engineers and scientists, we care about the orders of magnitude that are dropped. So a reduction in residuals from 2e to the minus 3 to 1e to the minus 3 isn't really something that we tend to focus on, because this can just be caused by differences in that representative heat flux passing through the bar. So all we need to do to scale our residuals is to just get some approximation of what the heat is flowing through the bar, apply that in the formula in 11, and that allows us to scale our residuals. So just to wrap up with a quick summary of what we've talked about today, remember that raw residual, when we calculate it directly from the energy equation, we substitute our current solution, T, into AT minus B, and that gives us the local energy imbalance in every cell in the mesh as a vector. And we need to scale this vector because the energy imbalances by themselves don't tell us anything about whether our solution is converged. So for example, an energy imbalance of 10 watts in a cell in the mesh, we don't know if we're very close to convergence or if we're very far away from convergence. If we have 10 megawatts of heat passing through our bar, then an energy imbalance of 10 watts means that actually we are very close to convergence. But if we've only got 100 watts of heat passing through our bar, then an energy imbalance of 10 watts in a particular cell is very large, and we're clearly not close to convergence. And what we're doing by scaling the residuals is giving us a percentage energy imbalance in every cell in the mesh. And then we can use the techniques that we used in the previous talks to get a representative residual for all of the cells in the mesh by using some normalization, say the L1 norm or the L2 norm, for example. And the scaling factor itself, this is calculated differently by different CFD codes. And so it's not essential that you have the exact formula and know how this is calculated, but if you want to, you often have to look this up in the CFD manual for your particular code for how the scaling factor is calculated. And because the scaling factor is calculated differently by different CFD codes, the scaled residual is not something that you should rely on the exact value to assess convergence. So for example, you can't say that a scaled residual of 2 times 10 to the minus 4, for example, is sufficiently converged, whereas 1 times 10 to the minus 4 is sufficiently converged. You can't do that because we can't rely on those exact values, because we're only scaling relative to a representative heat flux through the bar. And it's for this reason that we often look at other metrics as well when we're assessing the convergence of our CFD codes. And that's something I'm going to look at in future talks. So that brings us to the end of today's talk. I'm really hoping that with today's talk, you've actually built some deeper understanding for what residuals actually are when CFD codes calculate them. And you've now got a better idea that when you have a look at those famous plots of residual lines going down over time as the CFD code iterates, you've actually got a better appreciation that what this actually represents is it's a representative of the scaled residual for all of the cells in the mesh, and you're watching that scaled residual reduce as the CFD code iterates, and that gives you an indication that you're getting closer and closer to convergence. So I'm really hoping now that the pieces of understanding are starting to fit together and you're starting to get a bit of confidence with residuals and what they actually mean. Now, in the next talk, I'm going to be going further and filling in another key piece of information, and we're going to be looking at mass or continuity. And the reason we're going to be looking at this is this particular residual is actually treated slightly differently to the other transport equations. And by going through this one, you're going to get a better understanding of how it fits in with the overall picture of residuals and assessing convergence. So if you're looking forward to that next talk, let me know in the comments section. As always, drop some questions, let me know how you found the talk, and feel free to share it with a friend or a colleague if you think they'd find this talk on residuals useful as well. As always, thank you very much for your support, and I'll see you in the next video.